Hi everyone, welcome to the course of structural biology. Today this is a continuation where we will discuss about symmetry as in an overall concept and symmetry in crystallography. So, what is symmetry? Symmetry is called if an object or function is symmetrical if a spatial transformation of it looks identical to the original. Let us say this x is original. Now, if I make a 180-degree rotation and come to this, then I would say it is symmetry. But the interesting case is, if you see, you know that there is a 180-degree operation made, but because of the symmetrical nature of the structure, you do not understand it is a 180-degree rotation or a 360-degree rotation or a 0-degree rotation. So, what we need to see symmetry, we need a standard. With respect to the standard, your symmetry would be more pronunciably, more clearly understood. Let us say I put a red dot here, and now when I perform 180-degree, you see that the rotation happened and now this comes here. The red dot is not part of the system, not part of the symmetry, but the presence of it makes yourself clear. Similarly, a 360-degree rotation now would bring it here. This is a complex symmetrical representation where there are symmetries in some portion, some are not symmetrical. So, I have tried to put dotted white line. If you see on the screen, you will see that this part and this part are symmetrical. So, you see symmetry here, you see symmetry here, you see symmetry here in that way. Similarly, you get symmetry here because it is a hand drawing. So, the symmetries are not as perfect as we get here, but you clearly realize the symmetry. Similarly, here there is a symmetry, here there is a symmetry, but if I compare between these and these, they have a similar pattern, but they are not similar, they are very different. There is symmetry this side, there is symmetry between. Again, if you see, the symmetry is here, the symmetry is there, but between this part and this part you do not get the symmetry. So, this is kind of a presentation where we get complex drawings and all. What is symmetry operation? The symmetry of a molecules is essential for understanding the structures and properties of organic, inorganic compounds when we are talking about small molecules, but it is also very important for macromolecules like protein, DNA. Especially we are studying X-ray crystallography, you will see that the presence of symmetry. So, I will tell you there are two types of symmetries, one is crystallographic symmetry and other is non-crystallographic symmetry. What is non-crystallographic symmetry? Let us understand first. If I am standing here, a line could be drawn here. So, there is clearly two homogeneous or you say symmetrical part which form my body. That is what nature did, it did not come through the technique of crystallography or the technique of other symmetry operations. So, this is natural symmetry, non-crystallographic symmetry, something which comes when the atom is arranged in the crystal lattice, that is crystallographic symmetry. Why it is very important to understand? Just see this, you have a crystal where these dots are in identical positions. So, what you could do? You could take one but by solving the structure of the motif 1, you could apply symmetry operation, then you do not have to solve 2, 3 and 4 individually. So, your work is reduced to 1/4. That is the beauty of symmetry and its role in crystallography. The properties of chemical compounds are often easily explained by the consideration of symmetry. Let us take an example. The symmetry of a molecule determines whether the molecule has a permanent dipole moment or not. So, sometime we see molecules, right, like a water molecule, like a carbon molecule, being CH3Cl and a carbon molecule being CCl4 or a carbon molecule being So, in this way the set of carbon molecules would have different dipoles based on their symmetry and positions. The theories that describe optical activity, infrared and ultraviolet spectroscopy and crystal structure involve the application of symmetry considerations. The stretching, if you see in carbon dioxide, in normal condition, but because the directions, but if the directions are, if it is stretched, then generation of dipole. Matrix algebra is the most important mathematical tool in the description of symmetry, and we will see some of the operations. So, coming to the symmetry operators, a spatial transformation can be expressed as an operator that changes the coordinates of every point in the object the same way. Symmetry operators, the best qualities do not distort the object. In other words, the distance between any two points is the same before and after being moved by the symmetry operation would be identical. Here is the operator for a 180-degree rotation around the z axis. So, you see the around the z axis, it is the operation happened. So, x and y, there are changes x, y, z, minus x, minus y, z. So, these two are equivalent positions, and the concept come from 3 into 3 matrix multiplication, which have a matrix form like this. The elements of symmetry identified in the unit cell will be present in the crystal. So, which would be the symmetry? One, the center of symmetry, which we call inversion. Rotation, mirror, which is reflection, we will talk about them. Translation, translation is movement, and glide, which is a combination of reflection as well as translation. So, they are all referred to as symmetry operation. Now, let us see the symmetry inversion, where if you see all the coordinates are change x, y, z converted to minus x, minus y, minus z or minus z. So, there would be a point, and if you measure, every position would be equidistant from that. So, if this distance is this distance would be same. Similarly, this distance and this distance would be same. So, inversion provide a point from where everything inversed. Here also this is talking about the same thing. We have a point here, and from that point is acting as a inversion center. All the distances are identical. So, in the symmetry operation called inversion, lines are drawn from all point on the object through a point in the center of the object, which called inversion center. This is called a symmetry center, and it could be symbolized by I. It is also called inversion center, as I told. The lines each have lengths that are equidistant from the original point. So, each of the points here from this point would be equidistant from the two objects which we get from inversion operation. Coming to rotation, here in rotation we definitely have angles. So, x, y, z, there is change in according to the x and y axis. So, this is a representation of rotation. In the rotation matrix, it could be 2 into 2 for 2D, it could be 3 into 3, because in case of rotation, as we have seen here, this is 2D, it could be 3D also, which we will see. The product of any two rotation matrices is another rotation matrix. The inverse equal the transpose. So, R inverse equal to R transpose. It maintains orthogonality. The dot product of any row or column in the matrix with itself is 1. The dot product of any row or column with a different row or column is 0. The vector x, its absolute value equals to R x for any rotation R. Twofold rotation, here you see change in the two axis. So, this is a representation of twofold rotation which maintains phi2 symmetry. It is a 180-degree rotation. It called a twofold because doing it twice brings you back to the original where you have started. So, twofold axis here to here, the difference when you see rotation with reflection is the change. So, it would be the point from where the performance of rotation have operated. Equivalent position in fractional coordinates, I will explain what is fractional coordinate is x, y, z minus x minus y, z would not be there. So, z would be z, other two would be changed. Threefold rotation, as you see in the matrix, here you will see the changes, and in the fractional coordinate you will see from x it is converted to minus y, y to x minus y, z is not changed. It represents P3 symmetry. Okay. The equivalent positions are x, y, z minus y, x minus y, z minus x plus y minus x, z. Fourfold rotation, again it is a P4 symmetry. So, if you see x, y, z, it's changed to x changed to minus y. So, the position change, y changed to x, and z would be staying as z. So, its fourfold means it's 90 degree. When it was threefold, it was 120 degree. I didn't talk, I will talk about, but if it is sixfold, then it is 60 degree, like a hexagonal or a benzene ring. Rotation produces patterns where the original motif is retained. If you see the original motif, as I was talking about the hexagon here, in each case it is a sixfold. So, 60 degree rotation, and both original and rotation have the same handedness and they are congruent. What is congruent? I am going to explain it later. When the perspective will come, you will understand it even better. So, we have twofold, we obviously have one fold, the same thing, twofold, threefold. So, 1, 2, 3, 4, 6, 5. What happened to 5? Again we will see that. Rotational symmetry is expressed as a whole number n. Between 1 and infinity, n refers to the number of times a motif is repeated during a complete 360 degree rotation, which means if it is one fold, it is 360 degree divided by 1, the rotation. Twofold, the rotation is 360 degree divided by 2 is 180 degree. Threefold, 360 degree divided by 3, which is 120 degree. Fourfold, 360 degree divided by 4 is 90 degree. Fivefold, have an idea, is 72. Sixfold, 360 degree by 6, 60 degrees. In that way you will get. Rotation axis is 1, 2, 3, 4 or 6. Rotation of 360 degree, 180 degree, 120 degree, 90 degree or 60 degree around a rotation axis yields no change in orientation or arrangement. As I talked about, if you see here, you are rotating, you are further rotating, you are further rotating, you are further rotating. So, this is called rotational axis. You will more understand if you look at here. For a banana, there is one fold rotation, and one fold rotation operation implies either a 0 degree rotation or a 360 degree rotation and is referred to as identity operation. So, you have no symmetry, but if you take or you did not change, you definitely get the same. You make a 360 degree change, you definitely get the same for anything. So, this is one fold. Two-fold rotation, a two-fold is C2 rotation operation moves the object by 360 by 2 180. The symbol used to designate a two-fold axis is a solid oval. If you see, this is two-fold. Threefold rotation, a threefold or C3 rotation operation moves the object by 360 degree by 120 degree. The symbol used to designate a threefold is a solid equilateral. So, here threefold. Fourfold is C4 rotation operation moves the object by 90 degree. The symbol is a solid square. So, this is fourfold. Sixfold C6 rotation operation moves the object by 60 degree and this is a solid hexagon as I talked about. Coming to reflection, which is mirror. So, it would be change from one axis, x written x, y written y and z goes to minus z. This is one of the representation. You see the mirror plane and this is a very beautiful representation. This is the mirror you see. Now, see, if you have this, you have here. 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 So many planes here you see from the center how it work. Reflection, if you take a compound like this, remember I talked about these compounds CH2Cl2. So, the presented molecule contains two mirror plane. See, if you have a symmetry like here, you will differentiate between this CCl and this CCl, but if you have it here, you differentiate CH with CH. So, one is horizontal on the plane of the paper bisects the Cl CCl bond or so this is one. So, bisect like this. Other one is vertical perpendicular to the plane of the paper bisect HC H bond. Coming to translation. Translation is an operation denoted by T that generates a pattern in regular identical intervals. So, if you see, you go here, suppose this is the distance in the x axis, if I say x1 the same distance in the crystal. So, you go a translation of x and you generate one motif, again one motif, again one motif. If you go to z, so this is 2D, but it could be 3D. In a 3D space operation, translation could be labeled as xyz. So, you have 3 axes and their movement. In the glide plane, this is interesting. You have one matrix and you have second matrix, which tells you you have 2 operations leading to a result. So, x is x plus half, y is y, z is minus z. So, in the glide plane, it is a combination of reflection along with translation, reflection in z axis and then half translation. So, in geometry as well as in crystallography, a glide plane which is also called as transflection is a symmetry operation describing how a reflection in a plane followed by a translation parallel with that plane may leave the crystal unchanged. A very good example is this, where you see that here there is a reflection. If you put a mirror, you will have a reflection, but the reflection would be putting the feet here, but the feet is now proceeded. So, there is a reflection followed by a translation. A two-step operation, reflection followed by translation. Example of glide you see, and one of the very beautiful natural example of glide you will see when you go to any beach. You will see people walk. Generally, when people walk, they follow glide motion, because you have your one feet, the other feet is a mirror plane, but so it is a reflection, but it always proceed. So, you have your first feet, your second feet going ahead, that is called glide. Let us take a comparison to understand reflection and inversion. For that, let us look at this comparison purely in two dimension first. Reflection of a two dimension object occurs across a plane mirror. So, you see this is a reflection. So, here this point and this point are in equidistance, as well as this point to this point, but this equidistance would be going through this, whereas so the equidistance would be measured from the mirror axis A, B, A always equal to B. So, as A prime B prime. After inversion, everything is an equal and opposite distance through a single point I. So, if you see this is the point of inversion, you get those equidistance like you get here, but here through this point only, here through this axis, that is the difference. Now, we will discuss the combination of rotations. So, moving from 2 dimension to 3 dimension, which are the real system, multiple rotation axes may be identified. The rule is all symmetry operators must intersect at a single point. So, you have the rotations 2-fold, 3-fold, 4-fold, 6-fold, but along with that you should have the mirror plane. The combining of single operation rotation and inversion generates a roto inversion operation. This is a 3-dimensional operation. So, you have this picture. If you think of that diagram as two independent objects, you have a right hand in the upper hemisphere and you have a left hand in the lower hemisphere. So, you have a right hand and you have a left hand. The roto inversion is the symmetry operation required to transpose one object into the other. In this operation, rotate the hand through 360 degree. So, you rotate the hand from here to 360 degree and then you invert that. So, you have this, you do that and you invert. So, you get like this. So, you have like this hand, then you do that 360 and then invert, you will see that it would be like this. 2D inversion results in congruent pairs, whereas 3D roto inversion in enantiomorphic pairs. Remember, I did not talk about the congruent pair, but I told when the time will come. Now, it is the time when we are converting ourselves from 2D to 3D, because we always do 2D because 2D is easy to understand, but we have to do 3D because 3D is actual real system. So, in 2D inversion result congruent pairs, roto inversion in 3D enantiomorphic pairs. So, what are they? For a congruent figure or congruent pair, if the sides are the same length and the angles are equal, then the figures are called congruent. Each side and angle of one figure correspond to a side or angle to the other. We call these corresponding parts. For an example, the top point of one triangle correspond to the top point of the other triangle in a congruent pair like this, but it could be in different form like this also. So, this is also a congruent pair, and even when they are not having a regular shape, in that time also they could be congruent pair. So, congruent figures or congruent pair have exactly the same size and shape. They have congruent sides and congruent angle. Now, what is enantiomorphic figure or enantiomorphic pair? Pair of compounds, crystal, molecules that are mirror images on each other, but are not identical. So, you could see the pair of crystals, they are enantiomorphic pair. So, we talked about in the 2D inversion results in congruent pair, 3D roto inversion in enantiomorphic pairs. So, we already talked about, now you could put this on top of this, but now you understand we have already shown you in the model that this is a chiral pair and they are not superimposed like hands. If you want to put them on the top of each other, these two would not be superimposed. So, that is the difference between a congruent pair and a enantiomorphic pair. So, coming to another one, another roto inversion, this shows a roto inversion operation where n equal to 2. So, you do a 360 degree, but you do not do just the inversion as you are performing here, right. Here, instead of the combination of invert, you have twofold, that is the difference here. Coming to a 3 roto version, it returns the unit cell to its original position. Like you have here, you make 120 degree angle here, then what you do the next operation where you come here and then you have the right hand and you have the left hand. So, because it is threefold, you are making 120 degree rotation with the inversion. So, you see the changes in the picture with corresponding change of 120-degree angle with the inversion. So, total symmetry operation and their symbols, symbol E is identity, which means doing nothing. So, there is no symmetry element. C n rotation by 360-degree by n, which is n-fold axis, two-fold is 180, three-fold is 120, like that. Sigma is reflection, which demonstrate a mirror plane. I is a inversion, which is a point, and Sn is a improper rotation, which is n-fold axis and a mirror plane. Simple combination system combining various axes of rotation to generate three-dimensional patterns. So, two-fold rotation plus two-fold rotation, and this is a operation four-fold rotation plus 2 into two-fold rotation. Here you have the vertical two-fold axis in C operates at two-fold rotation on A. See the generation of a point which is B having the identical axis. Similarly, here four-fold axis generate three identical two-fold axis. Let us say from the point you have this three identical two-fold axis. Now, if we insert a unit cell, we can track that what happens as each symmetry operation is executed. So, we are putting a unit cell. Viewing the image from above, means on the top, four-fold axis which is 90-degree, four-fold rotation of the original RR motif results in the way we will see the change in the figure. Now, remember, thinking with respect only to rotation, this new pattern has two new independent sets of two-fold rotations. The first one we have highlighted and like this, and the set themselves generate the second set of two-fold rotation, which is indicated by the black marker. So, we start from here, then we have created initially we get a new pattern, and then this new pattern generate itself the second set of two-fold rotations here. I talk about fractional coordinates. The crystallographic coordinate system is defined by unit cell. The location of a point is defined by fraction of travelled from 0 to 1 along each unit cell axis, which we have talked about. But let us say here we have a fractional axis 0.33, 0.25, 0.55. So, the fractional coordinates are always measured parallel to each axis. The axes are not necessarily 90-degree apart. The crystal lattice is an example of translational symmetry. Equivalent positions are x, y, z and x plus 1, y plus 1, z plus 1. So, one translation in fractional coordinates. Space groups that have no other translational symmetry operations are called primitive space group and represent with a letter P, but space group have letters indicating the type of translational symmetry. S centered, so center based translation, F centered and I body centered, and all those gives rise to 14 Bravais lattices, which are divided into 7 crystal systems. So, the 7 crystal systems are cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic and triclinic. The cubic crystals have the shape of cube, tetragonal have the shape of square prism, orthorhombic rectangular prism, hexagonal 120-degree rhombic prism, trigonal parallelepiped, monoclinic parallelogramic prism and triclinic parallelepiped. From these 7 crystal system, who are the 14 Bravais lattices? For cubic there are 3 for, so cubic there are 3, for tetragonal there are 2, orthorhombic 4, hexagonal 1, trigonal 1, monoclinic 2, triclinic 1, 14. So, 14 Bravais lattices divide into 7 crystal system. Arrangement of lattice points in the unit cell and number of lattice points per cell. So, if it is primitive, there are 8 corners and effective number of lattice points per cell is 8 into 1 by 8, 8 points. So, 1, 8 into 1 by 8. For I, if you do not remember, go back, I is body center, centered at the body. So, 8 corner and 1 point for one body center. So, 1 plus 1 is 2. For F, it have faces. So, 6 face and 8 corners. So, 1 plus 3 equal to 4, and then for the C centered ABC. So, it have 2 centers of opposite faces. So, 1 for corners everyone is having, and then 2 into half because it is either A or B or C. So, 1 plus 2 is 3, sorry, 1 plus 2 into half, because you have the centers of opposite faces. So, contribution of half, so 2. Now, looking at the details of the 7 crystal system, what we talked about. So, here in the cube it have primitive, body centered, face centered. The conditions are A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degree. So, it is the perfect shape. The symmetry operations are 4 by m, 3 bar and 2 by m. Tetragonal, for tetragonal there is primitive and body centered. So, here A equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degree. Symmetry 4 by m, 2 by m, 2 by m. Orthorhombic, it have all the contributions, primitive, body centered, face centered, C centered. A not equal to B not equal to C, the hands, the basis. Angle alpha equal to beta equal to gamma equal to 90 degree. Symmetry 2 by m, 2 by m, 2 by m. Hexagonal, you will note that here only primitive. For the hands, A equal to B not equal to C, angles alpha equal to beta equal to 90 degree, gamma equal to 120 degree. As I told, there is only one type of hexagonal lattice, the simple, the primitive one. A single unit cell marked in blue along with a 3 unit cell forming a hexagonal prism, if you see. The symmetry 6 by m, 2 by m, 2 by m. Trigonal, it could also called as rhombohedral, it have only primitive again. A, in case of trigonal, A equal to B equal to C, alpha equal to beta equal to gamma not equal to 90 degree, symmetry 3 bar, 2 by m. Monoclinic, primitive and C centered. Here A not equal to B not equal to C for the sides, and A less than B less than C, alpha equal to gamma equal to 90 degree not equal to beta. The symmetry is 2 by m only. Triclinic, it is primitive, A not equal to B not equal to C, alpha not equal to beta not equal to gamma, it only 1 bar is the symmetry operation. So, as I told, unique cells shape cubic, tetragonal, hexagonal, orthorhombic, monoclinic and triclinic. Crystal system according to cubic, tetragonal, hexagonal, orthorhombic, monoclinic and triclinic. Here you see 6, but we have 7 because hexagonal class have 2, the rhombohedral form and the hexagonal form. The point group symmetry in the inorganic crystal, usually they have perfect shape which reflects in their internal symmetry. Point groups are originally used to describe the symmetry of crystals. Point group symmetry does not consider translation. Included symmetry elements are rotation, mirror plane, center of symmetry and roto inversion. So, when you see crystal with symmetry MMM, the mirror plane, set of points related by symmetry MMM and plane represented for the symmetry MMM, the mirror. So, point group symmetry diagrams. These are the available point groups. Not going into details, I rather come into the 3D symmetry. We have 32 3D point groups. It is grouped by the crystal system and it have consideration no center and it have consideration of center, which is the consideration of translation. For triclinic, no center, it is 1, center it is 1 bar, monoclinic 2 bar and 2 by m, orthorhombic 2 mm with center 2 by m, 2 by m, 2 by m, tetragonal 4 bar 4 mm 4 bar 2 m with center 4 by m, 4 by m, 2 by m, 2 by m, hexagonal 3 m, 6 bar 6 mm 6 bar 2 m, 3 bar 2 by m, 6 by m, 6 by m, 2 by m, 2 by m. Isometric 23 432 4 bar 3 m, like 2 3 4 3 2 4 bar 3 m, 2 by m, 3 bar 4 by m, 3 bar 2 by m. I talked about n-fold axis where n equal to 5 or n greater than 6, they does not occur in the crystal because in those cases there are overlaps, there are unfilled space which are not favorable for the formation of the crystals. So, the adjacent spaces must be completely filled to get perfect symmetry, which comes in the n equal to 2, n equal to 3, n equal to 4 and n equal to 6. Overall, there are 230 space groups, 32 point groups, 14 Bravais lattice and 7 crystal systems which we are discussed. But now, we have to talk about selective environment in enzymes or proteins, which is our focus. We already talk about chirality, we talk about the amino acids maintain chirality. So, you cannot get D amino acids, you only get L amino acids. Here I am going to talk about a interesting story. So, you look at this person who is standing or waiting at the bus stop. The bus appears, the bus have 2 doors, you could say front door and back door. The guy could avail both the doors, it have equal chance. Now, suddenly the guy have observed the driver, there is a beautiful driver. So, now the equivalent chances of front door and back door, to him the preference become front door. Similarly, in enzyme or protein, especially in enzyme, when it goes for the catalytic reaction, the choice becomes depending on the chiral environment. And also, when you are considering here, as I told, the 230 space group, it reduced to 65 for protein because of its chiral environment. So, we have talked about the basic symmetry, we have talked about how those symmetries are operated using matrix operation, we have talked about the importance of those symmetry, especially when they are in 2D we understand well, but when it comes to combination it is relatively difficult to understand, but they are the one which are actually present here. So, we talked about the combination, we talked about the operation, how that gives to a system of Bravais lattice which is having 14 crystal to a 7 crystal system which is there, the space groups we talked about, and we end up understanding the fact that in protein there are 65 space group instead of 230 because of the chiral environment present in protein. From here we will shift from direct space or real space to a reciprocal space. We will talk about Miller indices in the next class. Thank you very much.